Thank you very much for inviting me. It's a pleasure to give a talk here in this famous university. My title is on the board, and let me say it again. It's right-angled cocompact lattices in high-rank simple Lie groups. And before I say anything else, let me say that this is joined with Miklos Abert, who is also here, and our colleague Gelander from Jerusalem. And to begin with, I'll give the definition. What is a right-angled lattice? It's a bit misleading because they're the famous right-angled arching groups. And lattices in high-rank Lie groups are never right-angled arching groups. So what do we mean by right-angled? We just mean a group is gamma is right-angled if basically you can generate it by a sequence of elements such that they have infinite orders with order of Gi infinite, and each successive pair of them commuting. Oh. Okay. Is it readable? Hopefully. I'll try to use the white then. Yeah. Okay. So that's what we mean by right-angled groups. And the reason we are interested in this notion because we wanted to study rank gradient of lattices. So let me define that by d of g, by d of gamma. This is better. This is the minimal size of a generating set of a group gamma. Minimal size of a generating set for gamma. And what is rank gradient? Suppose I take a sequence of subgroups, sequence of subgroups of finite index. So each of them hi. And what is the rank gradient of gamma with respect to that sequence? Well, that is the limit, if it exists, of the number of generators of each term minus 1 divided by the index. Okay, so we take a sequence of subgroups of gamma, each of finite index. And if this limit exists, basically the number of generators minus 1 divided by the index of each hi, then we call it the rank gradient of gamma with respect to that sequence. And you can ask, okay, why should this limit exist? In general, it may not exist. But it will exist if this sequence is a chain. So we say that a chain if they are linearly ordered. So if we have this, etc. Okay. If they are ordered by inclusion, then we call it a chain. And in that case, then the above limit exists. Okay. And the reason it exists is because it forms a monotonically decreasing sequence of rational numbers. It's an easy exercise to prove from the Nielsen-Schreier inequality for number of generators of a finite index subgroup in another group, to prove that this is a decreasing, monotonically non-increasing sequence, and therefore the limit exists if you have a chain. And if you don't have a chain, there are easy examples where this limit does not exist. Yeah. Okay. So rank gradient has connections with several different areas. In first instance, it was defined by Mark Lackenby to study conjectures in hyperbolic three-manifold theory. And with Miklos Abert, we found a connection with cost of measurable group actions as well. So we try to, it's an open question to compute these limits for various famous naturally occurring groups, in particular for lattices in simple Lie groups. Okay, so here's our theorem that we proved. Before I go on, I want to state what we've proved. Okay, here. Now suppose that gamma be right-angled lattice in a high-rank simple group, in simple Lie group G of real rank at least 2. Yeah, by high rank I mean rank at least 2, real rank. And then this limit not only exists, but actually it's 0 for all sequences. Of gamma, well, we just want infinite sequences, so we want the index. We want the index to tend to infinity. I mean, we're not allowed to repeat the same group again and again. Okay? Oh, gamma. So whether this actually, I mean, this is definitely not true in rank 1, because in rank 1, lattices are generally so-called large. So they have a finite index subgroup which maps onto a two-generated free group. And then in a two-generated free group, you actually have that this quantity, if gamma was free, this quantity will be constant all the time. Yeah, and it will not be 0. So this theorem is definitely not true in rank 1. And in rank 1, actually, you don't have right-angled lattices in general. For example, if you have a hyperbolic group, it's never going to be right-angled unless it's going to be virtually cyclic. Okay?
Sorry. So the right-angled lattice is what? Is a lattice that happens to be right-angled?
Yes.
And so which Lie groups do you have?
Yes, well, that's my next theorem. Yeah, example. So is there some example here? So I want to point out that we actually want to, we suspect that this result should be true without right-angled. Yeah, but we cannot prove it. I'm going to formulate a conjecture later which is even stronger. Yeah, but can we give one example? Yeah. So the main purpose of my talk is actually to give an example. So no such examples were known before, as far as we know. So it was not known a single cocompact lattice. Okay. So the basic example, if you allow the lattice to be non-uniform, so that the quotient is not compact, is, for example, just this guy in SLN R3 is right angled. Yeah. And why is that? Because it can be generated by elementary matrices, and you can order them in such a way so that they pairwise commute. It's an easy exercise to generate it with the pairwise commuting sequence of pairwise commuting elementary matrices. Yeah. Okay. Now, so let me make a remark. So here, if gamma is not cocompact, okay, then this result is known. This is known. This is known, in fact, with at least 2 different proofs. This was known. Okay. So here's one nice proof. Is if you take there's a result by so in this case gamma has the so-called concurrent subgroup property in this case if G mod gamma not compact. Then in high rank Lie group, then gamma has the congruent subgroup property, and in that case, of course, these are all arithmetic lattices, and it was proved by Sharma and Venkataramana. That if you have a finite index subgroup in gamma, so I denote by F the statement that H is a subgroup of finite index in gamma, then H contains another subgroup of finite index with which is just generated by 3 elements. Okay, this is a quite surprising result, and the proof of that uses techniques from the proof of the congruent subgroup property for these groups. And then if you have this result, this if you want to generate H, what you do? First you generate M with 3 elements. And then you generate the rest, you generate H in the profinite completion of gamma, because you've already generated something of finite index. It's enough now to generate the H as in the profinite completion of gamma. And then, in fact, you can prove that the number of generators of H grows very slowly. It's at most O of log of the index of H, where the constant here depends on just on gamma. Yeah, and this result was proved by Alex Lubotsky. Yeah, so that's one way to get this result for not cocompact lattices. Another interesting proof that leads us to the idea of measurable actions is to use cost of groups. So it was known that, in fact, it's proved by Gabron that if gamma is right angled, then gamma has fixed price 1. Fixed price 1 means that the group gamma has fixed cost in every of its measurable ergodic actions on probability spaces, which are essentially free. So I don't want to define cost and fixed price because to take me too much time. It's not essential for my talk. But let me just point out that there's a connection between these notions and rank gradient that was proved by Miklos Abert and me. So we show that in case HI is a chain, in gamma, which is Farber, so this is a generalization of the condition that HI are normal with trivial intersection. A relaxation of this is a definition of a Farber chain. I'm going to define what Farber is in a moment. Then, in fact, the rank gradient of gamma with respect to this chain is exactly equal to the cost of gamma acting on its on the inverse limit of gamma mod HI on this profinite space. This cost -1. Yeah. So you can form the inverse limit of this finite sets, and this is a profinite space on which gamma acts by left multiplication, and that this is an example of an action of a group on a compact probability space, and there's this notion of cost that I'm not defining, which is invariant for orbit equivalence of such actions. And if it's a number bigger or equal to 1, if the group is infinite, and if you subtract 1, you get exactly this group theoretic notion. Yeah. So if you combine this with Gaboureau's result, then you immediately get the rank gradient is 0 for chains, yeah, and for Farber chains. Now, what is Farber? A chain is Farber if and only if. So the chain is Farber if and only if this action is essentially free. So HI is Farber if and only if gamma acts almost everywhere freely on this inverse limit. Okay? Okay. Another way to see it is for any non-trivial element of gamma, the proportion of conjugates of HI which contain it tends to 0. So maybe I should write it down. Yeah. For any gamma in gamma which is not 1, if you look at the limit, now you look at the number of elements gamma mod HI such that A gamma is in HI conjugated by G, and you divide by the index. This is 0. Yep. Okay? So if these HIs were normal subgroups with trivial intersection, then at some stage the numerator here becomes 0, and you get a sequence of zeros. Yeah. But so Farber just relaxes the condition of being normal in this case. What time is it? 37. Okay. So a good question is, what about not cocompact lattices? So this theorem will be not very interesting if we didn't have examples of new examples. And we actually, it's not easy to find cocompact examples. And here's one example that is new. Well, you take a quadratic extension of the rationals. That's the field. And then take its ring of integers. Okay. And then you take a 9-dimensional vector space over K, and they take a quadratic form in 9 variables, which is, well, the first 7 of them are just squared. And then you do minus square root of 2x8 squared minus square root of 2x9 squared. Yeah, this is a quadratic form on this vector space. The algebraic group is SOF. These are the matrices of norm of determinant 1 which preserve the form. The real Lie group is just the real points of this algebraic group. And this is isomorphic to just, from the way it's written, this is isomorphic to SO72. It's a rank 2 simple Lie group. And gamma is just the integer points. It's G of O. Okay, yeah. Because this quadratic form never represents a zero non-trivially over the rational numbers, over this field, as it's easy to see using the evolution where you can switch the signs and this becomes positive definite. This is a cocompact lattice. Yeah. And this group gamma is right-angled. Okay? So I should write. So in this so gamma is right angle. Okay, so this is an example of such a lattice, and we expect actually here's what expectation. We expect actually that every simple Lie group of higher rank possesses at least one right-angled lattice. So every higher rank Lie group should contain at least one right-angled lattice. Okay? But we cannot even show this even for open, the smallest possible case for SL3R. Cocompact, yeah, at least one cocompact, yeah. Thank you. We can't do even this case. And it's for those who know about lattices and Lie groups, though it's easy to see that definitely there exist cocompact lattices which are not right-angled. And even in SL3R, you can find examples coming from norm 1 elements in division algebras of prime index. So if you take
You said it's not right-angled, but it depends on the partition if it's right-angled, right?
Well, it depends on the choice of the generating sets, yeah? So it's, a lattice is right-angled if it has a sequence of generators which pairwise commute, right?
Okay, yeah, but once you have a cocompact lattice in SL3R, and maybe your generating set is not right-angled, how can you be sure that there is not another one?
I'll show you how an example where there's never one, yeah? So what you take is a prime number P, and you take, you're going to make a lattice inside SLP R, for example. And what you do, you take a division algebra of dimension p squared over q with certain properties such that it becomes split when you tensor it with R. You can choose your division algebra to be such. And then if you take the group of integer points and you take the norm 1 elements of this division algebra, then this is never right-angled. Okay? And I mean, you can cook up this example of any algebraic number field. And the reason is because the relation of commuting is actually an equivalence relation in such algebras. You see, if x commutes with y, this and x is not in Q, but they're inside this algebra, then this means that they generate something which is a field, but the only fields of this algebra are of prime degree. So they actually, the Q of x, maybe you cannot read here. So in that situation, actually Q of x is equal to Q of y. This is a subfield of degree p over q inside delta. Yeah. So if now z commutes with y, they'll sit inside the same field. Yeah. So you cannot generate something non-commutative by just taking elements which pairwise commute. Yeah. So that's kind of that's a limitation of this approach. But what is the nice thing about getting right-angle group is that we can actually prove more results than just applying it to Farber chains and the cost theory. So let me tell you about the convergence of invariant random subgroups. Okay.
Finite index subgroup of right-angled lattice. Finite index subgroup of right-angled lattice is not necessarily right-angled, right?
Probably it won't be. I don't have a proof that it is going to be. Yes. Okay.
Sorry, why do you need simple group? Simple group? What is simple?
A lot of this probably will work also in semi-simple. But for example, we're going to need a result from a paper, the so-called 7 samurai paper that is nice to state for simple groups. Yeah. Okay, so let's be more general. So this more general approach illustrates why right-angled is a better notion. So we don't want to deal just with chains, and we don't want to deal just with sequence of subgroups. So let's define for a group gamma, so an IRS on gamma, an invariant random subgroup on gamma, is a probability measure invariant under conjugation on the set of subgroups of gamma. So this just denotes the set of all subgroups of gamma. So if gamma is a topological group, a locally compact topological group, then this space is a compact space with respect to the Chaboutier topology. Yeah. And for us, we only have to consider, in fact, the following situation. Let delta be a subgroup of finite index of gamma, Here's an example. And then you define mu delta. This is the uniform distribution on the conjugacy classes of delta inside gamma. Yeah? So this is the uniform probability distribution on the set of conjugates. Yeah? So it's a kind of an invariant under conjugation, and it's a very simple measure. And in this, by RS of gamma, I would denote the set of all invariant random subgroups on gamma. And this itself is a compact space. And we have the notion of weak star convergence for distributions. Yeah. So another, of course, if you have, if n is a normal subgroup of gamma, then of course mu n will be just the Dirac measure on n. Yeah, just a special case of this, but even without relying on finite index, then there's only one conjugate of n, and then we have just a pointwise distribution, which just selects a normal subgroup with probability 1. So these RSs are, in some sense, a generalization of normal subgroups. Okay? So here is a theorem that follows from the 7th Samurai paper by, that's the 3 authors that we already mentioned, plus Nicolas Bergeron, Jean Rembault, and Ido Samet. And I'm forgetting somebody, because I have 6. And Jan Beringer, sorry. Yes. So here's a corollary, is the following. So this theorem is a corollary of the results in this paper. So if G is a high rank simple Lie group, and you take any lattice and then if you take and gamma n any sequence of finite index subgroups. Of gamma. And then if I define mu gamma n, this is the, and I'm only, and I want to be infinite sequence, so I want the index. And I want the index to tend to infinity. And then what happens is that the distribution, which are just these finite atomic distributions, just supported on the conjugacy class of each of these groups, converges in this weak star topology to the distribution, which is just supported on the identity. Yeah, probability. Okay. So this theorem, we have more general result of that in this in that paper, and it's really a consequence of one way to view it is a generalization of the Margulis normal subgroup theorem, because it tells you that there is no normal subgroup of infinite index inside gamma, because if there was, then you can actually you can actually take a sequence of subgroups that kind of will contain it all the time, and there will be no such thing. Yeah. And the proof of this theorem is, despite this elementary statement, the proof relies on the Stuck-Zimmer theorem. Yes. So now let's see what we can say about rank gradient again. But now for invariant random subgroups. So we define it for chains, but we can actually define it for invariant random subgroups. Okay. So suppose that you have an invariant random subgroup which is supported on the supported only on finite index subgroups. Supported. Okay. And then why don't we define a rank gradient with respect to this of this distribution by the following: define the rank of gamma with respect to distribution mu to be the integral of the number of generators of a random subgroup, well, -1 if you want, divided by the index d mu h. Yeah, and the integral is over all the subgroups of gamma. Yeah. Okay, makes sense. So if this mu was one of these guys, then it's actually so if mu is actually supported on the conjugacy class of a finite index subgroup, H, where H of a finite index subgroup in gamma, then trivially, this thing here, the rank with respect to mu H, is just the number of generators of H minus 1 divided by the index, yeah? Because this will be the same, right? I mean, this will appear, it will be, all the conjugates will appear, yeah? So all these numbers will be the same, yeah? Okay, and now the easy part of what is we get from right-angled condition is the following proposition. We can prove more general results, but this is sufficient for our purposes. Suppose gamma is a right-angled group. This is completely general, doesn't have to be a lattice. And then if you have mu n, a sequence of RS invariant random subgroups, all supported on finite index subgroups. Again, let me just write F to denote that these are really supported on the finite index subgroups. And suppose that suppose that they converge to the identity distribution, to the distribution on just concentrated on the identity, and then basically the limit of this rank of gamma mu n and tends to infinity is 0. Yeah. So if you take this result together with the the result that was the 7 samurai result that I just wiped off, that gives you an immediate proof that the rank gradient of every right-angled lattice in a high rank Lie group is 0, not just for chains, but also for any sequence of subgroups of increasing index, yeah, because you just put the two together. And it's a good question whether one can define some notion of cost that can capture the rank gradient limit, if it exists, not just for chains, but also for sequences. Yeah, but we just don't know how to define such limiting object if you have a sequence of subgroups rather than chains. And there was something I wanted to say. The notion of Farber, really, a chain, it's easy to see that actually a chain is Farber. That's something I should have pointed out. I define this notion of a Farber chain, but it's an easy exercise to show that if you have a HI Farber chain, then actually that's equivalent to saying that these distributions, the induced distributions on the conjugacy classes of each HI converge just to the identity distribution. Yep. So it's a generalization of the notion of a Farber chain, but not just for chains, but also for sequences. Yes. So Farber chains were introduced as a generalization of the Luke approximation theorem from normal subgroups to more general chains of subgroups. And I have to say that our 7 samurai paper also, once we developed this convergence of IRSs and we proved this rigidity result, then we applied it to prove a version of Luke approximation limits for the Betti numbers of lattices of cocompact Lie groups. Yeah. So I think, to me, the main problems are, one direction is to generalize this notion of how can one define rank gradient for arbitrary sequence of subgroups. Yeah. And one can also define it also for Sophic approximations. We have some proofs that then the right notion is probably the notion of combinatorial cost defined by Gabor-Elek. And we have some ideas how to push it using combinatorial cost for Sophic approximations instead of subgroups of finite index. And the other very interesting direction is to find more examples of right-angled cocompact lattices. Yeah. I have to say that even though it may seem very special, this generation, this notion of right angle looks very, very, very special after all, but that's the best known way how one can control the rank gradient of a lattice. I don't really know. One can prove it using cost, but again, the results using cost also use somehow right-angled generation. So finding more examples and maybe a different type of condition on a lattice which will force it to have fixed price 1 is also very interesting. Thank you very much.
Just a remark, you could have mentioned that the cost has been introduced by Henri, who is present in this.
Oh, I'm sorry. Yes, it was defined by Levitt. Yes.
How do you prove that this is item with this?
Okay, so from here, this group actually contains SO3. We actually use the fact that the rank is 2 here. I have to say the congruent subgroup property is known for these groups. And what we use is this form can be decomposed, and this lattice contains gamma turns out contains many copies of SO31 times SO31, yeah, so G, yeah. There are many ways to put these groups inside, and using the Borel density theorem, we can actually show that when we pass to the rational points, these groups are still infinite, yeah, and that gives you lots of commuting pairs, and then you start to move them around. You know, this maybe you can take another. Usually there are several different decomposition of the quadratic form into pairwise perpendicular quadratic forms with one factor the same, and here two different ones, and then you start to move them around. It's kind of very simple linear algebra at some stage.
Okay, so this one you can get. This is the infinite. The SO31.
Yes, they have infinite index. Yes. What we start is we start with one conjugacy class of elements, finitely many conjugacy, finitely many elements which are in one conjugacy class, and they generate a they generate a subgroup of finite index here, and we prove that they are related. So we find G1, G2, G some number which we don't know, which generate gamma up to finite index. And they have this form. They lie in this, we pick a conjugacy class first. And then if you take the whole of the normal closure of one element with this decomposition, it will generate a subgroup of finite index in gamma by the Margulis result, yeah? So then you can define, then only finitely many of them are sufficient to generate a subgroup of finite index, yeah? So, and then we just use this approach to, because now they have this form. These elements can be chosen to lie in these conjugacy classes. You can start with any conjugacy class. And then we find intermediate sequence of elements of the same form which connect them. That's how we do it. But the start is basically the Margulis normal subgroup theorem, which says that if you take a normal closure of a conjugacy class, yeah.
In fact, this number 9 is the smallest you can get, right?
That's how much that's the freedom we need for our proof. I believe probably we can, maybe can do it for smaller numbers if they're clever. But we just wanted one example. Yes?
Just a comment. We conjecture or expect that take any fixed higher rank simple Lie group, then for any sequence of lattices, the rank grows sublinearly in the covariance. So we don't know a counterexample to this. So this could be an even more general theorem. You don't have to put it in one lattice. It can be any sequence of lattices. So the rank should grow sublinearly. We expect to be.
Yes. Have you considered something a bit different where you just leave a tree of commuting relations as opposed to a linear sequence?
Yes, it will work, yes.
It is more flexible, so there could be examples which have this tree of commutations, but not a segment.
You're right, yes. But if you have a tree, you can actually make it into a path and kind of traverse it with a stupid we can do repetitions, yeah? I mean, yeah, we can just repeat them, yeah.